since I think the next exercise is pretty long, and I received already some questions for the last exercises, I would say we skip the theory and go directly to the exercises. It's okay. So yeah. So today we're looking at the pulsating blood flow in the femoral artery of the leg. So exactly what you saw in the last picture of the presentation at the end. So let's go through the slides are anyway online, so you can go through at home. So this is exactly the same. So we have a femoral artery of a dog, and now I don't remember how he's called. So McDonald, a person, decided to both measure the pressure drop and the blood flow during one cycle of the heart. And what we want you to show is that with some MATLAB equation that I gave you, or function that we give you, that we can could approximate the pressure drop. No, the other way around. No. So if you have the pressure drop equation, you can good approximate the flow. So with the P function that you get, you can approximate the Q1 pretty good. Yeah. So it's a lot of MATLAB and one exercise that you need to calculate stuff. All the function that we give you, it's already online. So I hope you know how function works in MATLAB. Otherwise, you can ask. But they are also described on the top, so you can read what they do and what you need to put in and what you need to put out. But what I would suggest you start a new MATLAB file and then you recall the function that we give. So, first of all, you obviously cannot only get the pressure gradient. What you also get is those physical parameters. So we are at 3 millimeter in diameter. You have a velocity, which is the blood flow velocity. We will look at it exactly, I think, next week or the week after, how we can get this number to calculate it yourself. And then all the same to what you normally get, and the frequency 1 heartbeat. What I would suggest you is to use 1 heartbeat for your simulation. Don't do 3 or 4, just use 1. So the problem 1.1. So you need to estimate and plot the pressure gradient as a function of time using the pressure measurement. So you have the pressure gradient function, and there you need to put in the time that you want this pressure gradient and plot it. So I don't have open it, but it's not difficult. So the pressure gradient only asks you amount of times that you want, and then you can plot it. You receive the function and you can plot it. And again, please use only 1 heartbeat. It's the best for this. And yeah, that's, I hope, not too difficult. And then, so then you need to have the average flow rate. So you need to think which formula do you want to have to calculate the flow rate. So there is a little bit of thinking, but we are here thinking about the average. So over 1 beat, how much flow rate do I have? And for that, you also need an average for the pressure drop. And yeah. And then the last one, you want the physical flow average rate. And to obtain, you need to take out this piece of there is a shift, as we saw. in the pressure, between the pressure and the flow rate. So you take out the shift as the formula there. And important units again. This is millimeter of Hg and not Pascal, so be careful of that. And then plot it and just think what are the differences, so what it's happening, and so this is the first source. So yeah, and this is the pressure gradient that you need to use. And for this, for the second problem, still continue your MATLAB script, don't start a new one, go on with what you had. And here we don't want to have the average over time, so we want to calculate the Q. So defines your Q equation depending on delta Z, delta P over delta Z, and then plot it. I think you should know which formula you should use for that. And then what we want you to do is to compare it to the external measurement, which is there is another function that you have, which is Q, called Q, and that's the same. The points that you have for your flow rate that you calculated, put it in this other function, plot it both together, and then you can see, is there a difference? Are they exactly the same? Obviously, they are not, because R is an assumption, and his are really measurements that he did. So I want you to think, what is different? How can we change it? What assumption did we took that are not entirely correctly or can be changed? So yeah. And this is what we want you to look in the problem trace. So again, continue your MATLAB script. First, you should calculate the Walmsley number, as we saw that gives you a lot of information on the shift of the Q and so on. So please first calculate the Walmsley number, and you need to plot the absolute value of the complex velocity and angle, which I hope you know how to plot it. And for that, you use Walmsley. So there is another function for you given where you need to put in some stuff, and then you receive this Walmsley number. And from there, you need to plot the angle and the complex and the velocity angle. And so here we are looking at, before we were looking at like a flow. And for this, it's like you cut your pipe. So the Walmsley number, what you need is a grid over your pipe. So what you want is to know the a plot where here you have your zero, E hat, and D hat. Well, you can also plot it the other way around, but what you want is that here you have the absolute value of the phase angle, so phase angle, which is not equal over the whole radius. You saw that it's the shift of the pressure gradient and so on. It could be something like this. So it depends on the radius. So here we are not looking at time, we are looking at the radius. So what you need to put in that function is like a grid over the radius. And the same for the complex velocity. So sorry, this is more the complex velocity. For the first part. And then when you calculated alpha, you can then use those two graphs that you saw at the end of the lecture to calculate back the phase lag that you have in that vessel, and also the amount of Q that you are able to push through the vessel, as we saw that when, depending on the frequency, we can push more or less flow into the vessel. And with those two information, so you calculated alpha, you can integrate in your function that you had in problem 2 at the end. You can integrate on phase shift and the Q, and then you can see, oh, okay, my Q at the end is different. Is this equal? So plot it again against your first Q, the Q of McDonald's, and this one, and see again, oh, what shifted, what is better, what is worse. Yeah, did we arrive at the same solution as McDonald's? So, yes. I think this was problem 3. So for problem 4, what we want to compute is the actual flow profile. And for that we need this Walsh stresses. So this is not the same function. So this is another function that I gave you. You can change it directly in this function. The thing that we want you to do is to compare. So you need to calculate you need to compare this equation that you have here, which you can put it in directly in the MATLAB script, plus the one that you calculated. So you can compare it to the Poiseuille theory. So this omega on top here, the omega here, the omega there, which is the velocity, you can compare it with the Poiseuille flow. So use this equation and the Poiseuille flow equation where you insert the omega of the Poiseuille flow and compare them and plot them together and see what difference do you find and so on. Okay. There's problem 5. This is more difficult, which I saw last year. A lot of people had problems, mostly for me because they didn't know really well what they were supposed to do. But I can present it to you. This is not MATLAB anymore. What we want you to do is calculate the boundary layer, which depends on the flow. So here we are not looking like a pipe. We are taking in consideration we are expert in that, but consider an infinite plate. So we have a plate, which is not like that. And here it goes on infinitely low. This is X, and this is Y. And this plate is moving parallel to this plane, which means it's not moving like this, but it's moving like this. Back and forth with a specific frequency. Yes, the frequency is there. So with more than 0. In this direction. And what we want you to do is to plot the changes in this is the boundary layer. You have a boundary layer in the x direction. And it's a lot of calculation, I know. And you have those boundary conditions there so that you know that here the velocity is u0. But here we have a velocity of u0 of omega. And here we go to infinity, we have u equals 0. So you need to make some assumptions. So what I would suggest you is to start with the Navier-Stokes equation, divide it into so x and epsilon, and then start with some assumptions. So you know that there is no velocity of the fluid in this direction. So v is always equal to 0. And then some stuff pull out. What else? Yeah, I cannot say everything, otherwise I do the exercises for you. But yeah, start and thinking. If you start with the Navier-Stokes, you put so I would divide them like u plus u becomes like the x and so on. And write the same for the this would be u equals and if you start with that at the end, you can arrive at a solution. One thing that I can tell you maybe is that at the end you have something u u squared or something in that direction. Something like this. And to solve this, you can take the ansatz that u is the real part of epsilon, so a function depending on epsilon multiplied by e. Since we know that it's dependent on the frequency, e omega 2. So the real part of this. And what I should suggest you is to, so you know that e elevated by something can be written in cosinus and sinus. And there is an e in there again, take only the real part of that. And then you can solve and you arrive at the end, the function, which is, well, that's a lot of math. But at the end you can have and then it's what we want you to do. We know that the velocity here is 0. Here is this velocity here, and on top here is somewhere 0. And what? Sorry, this is an epsilon. Well, and there is a MATLAB file that then plots you the velocity, and then you can also see the boundary layer. And to do that, you can take inputs and think where does the u0 becomes 0.05, I think. 0.05. And from there, you can calculate this boundary layer for 0.05. And you arrive at an equation that is dependent on something that I think yeah, it's depending on omega and tau. And what we want you to do is then plot it in the Stokes boundary layer. You can really see how it changed when the plate shifts. But yeah, it's, I don't know, maybe you have done it, is the Stokes second problem. But I don't know, people were like, what is moving? and so on. I was like, so it's written there. But yeah, there's this, so you may consider a plate that moves. Here you have the velocity, and the velocity in this direction there is none, obviously, because this moves only. It's a long, my solution is a lot of pages, but it's good to do because you go really through it and really think, what condition do I have? What can I eliminate? What not? And the last, and well, and use that in. I hope you know how to. So, and the last one is more a thinking question. Nothing simulation, you don't need to plug anything. It's like if we replace our human heart with a normal, how do you say it? An artificial bone, which normally doesn't have a pressure, so it doesn't have this frequency. It's like constant flow. What happens? What are the difference to our heart? And at the end, if you think about it, you have less stress in the heart vessels and so on if you have a constant flow and you don't have these peaks. And think a little bit about again, why do we have a pumping heart and not a constant flow? So it's just thinking questions that why our body does something very difficult and not could have done something easier. Yes. That's it for the problem. I know it's long, a lot of MATLAB and a lot of calculation, but I think it's good for you to really think and also visualize with the MATLAB what you are doing, what if I shift this, what happens. So for the exercise, yes? No. So MATLAB will not be asked in the exam. That's not the goal. What we want you now with MATLAB to do is say, okay, I shift this shifts this. So if I give you a plot, and then I say, okay, this is the plot. If I have an alpha bigger, what happens? You should be able to do it. We don't want it precise, but you should know, okay, it becomes shifts to the left. So we need to see a shift to the left. If it's 1, 2, or 5, no, it's not what we want. I mean, we're not asking MATLAB, we are not in MATLAB class. But it's a good tool to visualize what you're doing. And yeah, it's really important to know what happens if you shift something, but exactly how does that happen. You don't need an laptop. So, for the exercise 2, which one do you want to do? The first problem or the second problem? I have both ready. Oh, I forgot to. Lost my. You see it. So, which one do you want to do?
I have a question about the second part of the first problem, but just a small one.
Yeah, as you wish. I mean, or we can do questions, because I mean, you have the solution, or we can solve it together. What do you prefer? You should say. I mean, we have not a lot of time left, so maybe question is better. Is that okay for everyone? I mean, you can always write email. I will respond. Maybe not in the second that you send it, but let's do it like this. So what's the question?
Can you lowering
yeah, that's I have received a lot of questions.
It's just the mean velocity. That was right. Yeah, you understand. Go ahead.
Yeah, so so what? So I hope you we have also the velocity in the boundary layer. You can write it as A multiplied by the radius plus B, right? And you know that so when R is equal to theta, you have omega equals 0, and when R is equal to you have lambda of the okay. And if you solve this, I hope you know how to solve this. This is basic math. You arrive to at the velocity equal velocity net force divided by just multiplied by r minus the velocity with themselves divided by 2 which you can also write okay. And then what we took is the mean of it, since it's line, so it's a steady state. The mean of this is mean as normally 1 divided by the layer that you're looking at between the D divided by 2 and to D divided by 2 by this cells. Okay, and from here you can calculate it, so this is not dependent on the radius, it's only this part. So if you do the integral, this will, I hope you know. And at the end, everything closes down and it comes to at the end what we have. We read those files divided by 2.
This is the example.
Yes. If you do this, you're right with this. You try it or?
But because it's a linear gradient of the velocity, right?
Yeah.
So, even if you don't do any calculation,
you can see this is the mathematical. You can put it in and say, okay, it's really like this, but you can also think, yeah, I mean, the mean, if we go on.
What I was meant to say is you can say that the new velocity shouldn't be half-constant.
Why not?
Because there is more flow on the outer side than in the inner side.
Okay, if you look at the whole pipe.
Right.
Yeah. Yes, but since we said that this is really smaller than D, the difference between the really outside and the boundary layer is so small.
Then you feel like it's some kind of thing.
Yeah, then you can do some kind of thing.
Because if you do, there should be like a different factor in this flow.
Yeah, it should be a little bit less because you have more flow that doesn't flow. But since we said at the beginning, it's the boundary layer is so small that at the end the difference in the area from the flow where it's 0 and where
I understand that we can do this implementation, but I just think it's unnecessary because you can easily calculate the precise one. So
yes, you can. If you want, you can do it everything with a precise one, and then have factor in that you wanted to get it. But we are not that math class that we want to. So that's why, and I think we took it out many times when we knew that if the boundary line is really smaller, we also left it out already before. So yeah. Other questions? Was it difficult for you? Did you do it? Or only wait for the solution?